Hello, so in this video we're going to be learning about chemical reactions. Before we talk about the specific chemical reactions that I'm going to go through today, I need to tell you about a big important law in science, and that is the law of the conservation of matter. Perhaps in physics you remember the conservation of momentum law. There's also a conservation of energy law, which we're also going to look at. But the idea of conservation is keeping things the same. And in chemical reactions, the amount of mass that you have, that you start with in a chemical reaction, you'll end up with the same amount of mass. So for example, let's say that you react two things together and you start with a total of 50 grams worth of matter or mass, then you'll end up with 50 grams. The idea of chemical reactions is that there'll be some kind of change. So one or more of the substances will be changed into something else permanently. And so, but the amount of mass that you start with is equal to the amount of mass that you end up with. Also, the starting ingredients or the reactants in a chemical reaction, those things will end up in the products as well. So let's say, for example, you react hydrogen and oxygen to form water. You can't end up with water and helium at the end of the reaction because you didn't start with it. So part of this law, the conservation of matter law, is the amount of mass that you start with is the same at the beginning and at the end, and also the types of elements that you have in that reaction stay the same from beginning to end. There's going to be some change, rearrangement of atoms, different bonds are going to be formed, broken then formed, but the number and type of elements is going to remain the same. So I'll try and give you an example of that. So if you think you're going to think of making a peanut butter and jelly sandwich like all good Americans, so you start with a serving of peanut butter and you get a serving of jelly. So one serving of peanut butter, one serving of jelly, plus 2 slices of bread. You mix it all together and you get one PB and J sandwich. So you only have enough reactants or ingredients to make one sandwich. So you can't end up with 5 sandwiches because you don't start with the amount of reactants to get 5 sandwiches. All you have is the ability to make one sandwich. Also, you don't have egg in this sandwich. That'd be pretty disgusting for one thing, but also you don't start with it as an ingredient, so you can't end up with it. You can't magically create an egg out of these ingredients. If you can, high school chemistry isn't for you. You should be at NASA. So these are the ingredients that we're starting with. The amount that we have is going to be the same. If this weighs 25 grams, then the sandwich itself is going to weigh 25 grams. We don't have any magically appearing elements or substances in the final product because we didn't start with them. So that's the idea of conservation of matter, and it's also called the conservation of mass. And then also what we'll do is in class we'll look at the conservation of energy. So the amount of energy in a reaction stays the same. So So the idea of chemical reactions is that one or more substances are changed, and the way that we describe the ingredients, reactants, products is what you end up with. So you can think of reactants as the ingredients to make something, and the product is what you end up with. So there are 6 main types of chemical reactions we're going to look at. There are more, but they'll come up later on. Synthesis, decomposition, single replacement, double replacement, combustion, and redox. So we've already spent quite an amount of time on redox already, so we're not really going to cover that too much in this video, but we're going to look at these chemical reactions, and then I'm going to also show you how to balance chemical reactions using an example from each type. Okay. So synthesis, as the name implies, you take 2 or more substances, combine them, create a new substance. So a good example of that is making our old friend dihydrogen monoxide. which is water. So we've already started to look at this convention of writing reactions when we did redox, but just to go over it again, what we're saying here is that you take this and you react it with this, and it yields or gives you H2O, or yields products. So the arrow means yields, it gives you, fancy chemical name for produces or gives you. So these symbols down here, hydrogen is a gas at room temperature and pressure, so the G stands for gas. Same here, and then the L stands for liquid. In your notes, you're going to see another couple of abbreviations for the states of matter that the substances are in, because it is important. For example, if you just take H2O gas and gas, you don't create solid water as ice, really, you create liquid water. So in some reactions it's very important that you specify what state of matter the substance is in. And it's just we use the parentheses as kind of a subscript with the state abbreviation. So that will be a synthesis reaction. So how do you balance that? Well, the idea of the conservation of matter law says that the number and type of atoms you've got on the reactant side must equal the number and type of elements, atoms on the product side. So I'm going to list out all the different elements that I have. So on this side, on the reactant side, I've got hydrogen and oxygen. I'm going to label these as reactants and products, so I don't get confused. So first of all, if the elements that you have as reactants aren't in your products, then something's gone wrong. So these should be the same. Also, another golden rule about balancing reactions is that the formula should already be written. So H2, it's a diatomic molecule that exists as a pair, so does oxygen. And then H2O, we did crisscross balancing the charges, so 2 hydrogen ions, with 1 oxygen. So how many of each type do we have? And then that's going to help us balance it, hopefully. So this 2 means I've got 2 of these bonded together, so that's a total of 2 hydrogens. I've got 2 oxygens here, same idea, 2 times this, or 2 bonded together. In H2O, I've got 2 hydrogens, and then 1 oxygen. So my number of hydrogens is equal on the reactant side and the product side, that's good. The oxygen, though, is not balanced, it's not equal, which can't happen, because I started with 2, so where did the other one go? Well, it went somewhere. So what I need to do is change that to a 2. I need to increase this by 2, and to do that I need to put a number in front, so that shows more oxygen, preferably 1 more. So the only place I can put a number is in front, up here. If I put a number down there, that means a completely different substance. That means H2O2, 2 hydrogen, 2 oxygens all bonded together. That's not what we have. We have H2O, so we only have 1 oxygen in this molecule. So the only place I can put a number, I can't mess with the subscript, so I've got to put a number in front. And then you can think of this as like algebra. So to use distributive property, it's 2 times the x, then 2 times the 1. You can think of it that way. We don't write it that way, but maybe in your head you start thinking about remembering distributive property and how much you love algebra. So what I'm saying here is I'm multiplying the number of hydrogens by 2 and the number of oxygens by 2. So I fixed my number of oxygens, which was good, but 2 times 2 hydrogens is going to actually give me 4, which is bad, because I've only got 2 hydrogens on the left. So what I need to do is increase my number of hydrogens on this side, and so I do that by putting a 2 in front. 2 times 2 is going to give me 4. So the big idea here, this is a synthesis reaction, so we've taken care of Synthesis, you take two or more substances, in this case it's two, react them together, create one new substance. I needed to balance the number of oxygens and hydrogens that I had on both sides. I did that by listing out my reactants and then my products and then the numbers of each element, and then making sure that the numbers were equal on both sides. So that's synthesis. So now I'm going to do decomposition. And you can almost think of decomposition as the opposite of synthesis. And I'm going to use the same example. So decomposition is you take a substance and it breaks down into simpler substances. For example, let's say we take H2O, and it's a liquid, and we decompose it into hydrogen and oxygen gas. We didn't do this yet in class, but you actually can run electricity through H2O, and you actually get the gases produced at the different electrodes, and we will do that in class, but quite an easy experiment to do. So we take water, put some energy into it, decompose it, it yields hydrogen gas and oxygen gas, which makes sense because you've only got oxygen and hydrogen in there to begin with, right? You couldn't end up with carbon on that side because you don't start with it. So, very similar reaction. I'm going to write out my number of reactants. 1 oxygen, 2 hydrogens. On this side I've got 2 H's and 2 oxygens. So, I'm going to put a 2 here because that number of oxygens needs to be balanced. My number of hydrogens increases to 4, 2 times 2, so I need a 2 in front of the hydrogen. So same sort of idea, you're balancing the number of each element on the reactant side and the product side, making sure they're equal, and that would be decomposition. So single replacement, and actually all of these reactions we've actually done in class already, but we're just going to give like an official title to them. We're going to show you more examples and then show you how to balance reactions, which is a really important skill. Later on in this class we'll look at more about chemical reactions, and so we're kind of getting an introduction to some of the types of reactions and how to balance them, which will be a really important skill later on. So decomposition. Now let's look at single replacement. So single replacement is when you take a single element and you replace it with another element that's already in a compound. So for example, let's take zinc, which is a solid. And we actually did this experiment in the Penny Lab quite a long time ago now. But you take zinc and you react it with hydrochloric acid, HCl. So zinc is a solid, hence the S. AQ stands for aqueous solution because hydrogen chloride is dissolved in water. And that yields zinc chloride and hydrogen gas. So zinc chloride is actually a solid, it's a white ionic crystalline solid, but because it's dissolved in water we don't see it necessarily, you don't really see anything in this reaction apart from the hydrogen gas being produced and the zinc disappearing. So the zinc gradually turns into zinc chloride and this hydrogen gas bubbles away. So that's the effervescence that you see when you do this reaction, or when you take the pennies and you put a slice in it, leave it in the acid overnight, and all the zinc dissolves on the inside. So then the single replacement aspect of this is that the zinc has replaced the hydrogen. So zinc replaced hydrogen over there. So then to balance it, we go through the same steps. List out the different reactants that I've got, zinc, hydrogen and chlorine. On the other side, I should have the same, and I do, which is good. Another tip when you're balancing reactions, if you write each substance in the same line, it helps just keep it clearer. So listing out all the different reactants and products, now I'm going to count how many of each one I've got. So I've no numbers close to the zinc, or same with the hydrogen and chlorine, so they're all 1 each. I've got zinc and chlorine, so that's 1, and then 2 of those, and I've got 2 hydrogens. So there's a couple of things that you need to remember. So how did I know to write zinc chloride like that? Well, this takes into account that you already know how to write formulas, and that if you don't, then you go back to the polyatomic ion list and you look on there and you write the correct formula. So you should have already realised that zinc is a 2+ ion, chloride is -1, so if you do crisscross, this is zinc chloride, and hydrogen exists as a diatomic molecule. That's something that you just need to commit to memory. So I'm not balanced here because I've got 1 zinc, which is okay, and I've got 2 hydrogens, 1 hydrogen, 2 chlorines, 1 chlorine. So how will I fix it? Well, I'm going to put a 2 right there. So that takes care of hydrogen and chlorine, and I'm all balanced. So, single replacement reaction, the zinc replaces the hydrogen to form zinc chloride, and then the hydrogen is left over, and hydrogen always makes a diatomic molecule. It doesn't exist as a single atom, so that's single replacement. So double replacement is kind of similar, but as the name suggests, you replace 2 things rather than just 1. So double replacement, let's use an example. Let's take barium chloride. So this is the test for sulfate that you did in the chemical identification lab. So you take barium chloride solution, it's AQ because it's dissolved in water, and then you're going to react it with a mystery substance, and let's say that substance is copper sulfate. So copper sulfate is the blue crystals, makes like a blue, clear blue liquid. So the test for sulfate is to add barium chloride to copper sulfate, or to a sulfate solution, and then we get barium sulfate, which is an insoluble salt. So then on the other side of this equation, we're going to get barium sulfate, and that's a solid because it forms that white precipitate. And then we also get copper chloride. I'm running out of room, but that's okay. So a double replacement. So in this case, the cations have switched places. So barium chloride and copper sulfate went to barium sulfate and copper chloride. So another difference here is that the barium sulfate is insoluble, so it doesn't dissolve in water. So the AQ means you've got loads of water molecules in here, but this doesn't dissolve, so it just stays as a solid. So this is the test for sulfate that we did in class. So it looks kind of scary because you've got all these different numbers in there this time, but basic same principle is going to list out the different substances and make sure they balance on both sides. I'm going to show you a really nice little trick here to deal with the sulfate. Rather than try and split it up into sulfur and oxygen, we're actually just going to keep it as one unit, and it will make life so much easier for you. But we have barium, chlorine, copper, and sulfate. So I didn't list out sulfur and oxygen. Perfectly okay if you do that, but this way is a little bit faster, and I think a little bit easier. So there's barium, chloride, copper, and sulfate. So now you're going to look at each line and make sure, or count up how many you have on each side. So barium, I've got 2 chlorines, 1 copper, and 1 sulfate. On this side I've got 1, 2, 1, and 1. So that was easy. So in this case this happened to be balanced already, but this is how you check, right? This is a really almost foolproof way to figure out is your reaction balanced, and if it isn't balanced, how do you balance it? So again, double replacement, the idea is that either the positive species or the negative species switch places. In this case it's barium and copper switching places. So barium chloride and copper sulfate went to barium sulfate and copper chloride. We balanced it the exact same way. Neat little trick to deal with the sulfate as one unit because it ends up on both sides. So that's a good trick to remember. So the last one is combustion. So combustion is about burning. It's very specific. So other substances burn, but we're just going to look at combustion. And the definition for combustion is that you take a substance called a hydrocarbon. And a hydrocarbon is a general way to describe any substance that contains hydrogen and carbon. So a lot of organic chemistry, what else? So propane that you use in like in a grill, gas grill, is a hydrocarbon. It just contains carbon and oxygen. Butane in cigarette lighters is another one. Methane, another example. So hydrocarbons are used as fuels quite a lot. And the nice thing about hydrocarbon and about combustion, is that the general reaction always has the same products. So the definition of combustion is that you burn a hydrocarbon, and I'm going to write one in there in a second, but the general form of it is you burn it in oxygen, which is O2, and it forms carbon dioxide and H2O. And these are both gases. So whatever kind of hydrocarbon, propane, butane, methane, candle wax is paraffin wax, and that's just a hydrocarbon. It's made up of, well, maybe some dye and some perfume, but mainly carbon and hydrogen bonded together, covalently bonded together. So any hydrocarbon can go here. You burn it in oxygen, and you form carbon dioxide and water. A lot of the fuel, burning of fuel follows this reaction. Our bodies burn sugar, which is glucose, and the oxygen we breathe in, and then we breathe out carbon dioxide and H2O. So this reaction is very, very common and very important, otherwise we'd all be dead. So let's use methane as an example. So methane is CH4. So you take methane and you burn it in oxygen or in the air, right? Because there's loads of oxygen in the air. Nitrogen is about 3/4 of the air that we breathe, but it doesn't react with anything. But the thing that does is oxygen. And then carbon dioxide and H2O are our products. So we're going to balance it the exact same way. But one thing to remember about combustion, this part of it is always the same. So you see combustion, you're already thinking, I need O2 and I get CO2 and H2O. The amounts of each is going to change depending on the hydrocarbon, but the basic reaction is the same. So I've got carbon, hydrogen and oxygen, CHO, and the same on the other side. So the trick here is to realise that in this case you've got oxygen in different places. So it's a really easy place to trip up. But just remember that you've got 2 oxygens here and 1 here, so that would actually give you 3. 1 carbon and then 2 hydrogens. So then on the other side we've got 1 carbon, 4 hydrogens and 2 oxygens. Okay, so this time I've got quite a bit of balancing to do. Carbons are the same, that's okay, but the other things need some work. So ignore carbons and just go straight to balancing hydrogen. And in this kind of reaction, this more complex balancing, just do one thing at a time. Try not to fix everything all in one go, because that's too confusing for one thing. And as you add more complicated molecules here, it gets easier to make a mistake and to lose track. So just do one row or one line at a time. So hydrogen, I need to double the amount of hydrogens over here. So I'm going to put a 2 right there. So 2 times 2 would give me 4. But now I've changed the number of oxygens. I've got 2 times 1, which is 2. And I've also got 2 there, so that's 4 total. So I need to double the amount of oxygen over here, and I'm going to do that by putting a 2 in front of the oxygen. So now I've got equal numbers of both. So that's combustion. Follows the same general pattern every time. One potential way to get confused about combustion is to think that everything burns. We don't classify everything as combustion, even if it is burning. The combustion reaction is this. For example, if I took some magnesium and burned it in oxygen, then that forms different substances. It doesn't form these two things. So that's not falling under the definition of combustion. That would actually be redox. So if a reaction isn't any of these things, it's redox. And also redox reactions can also be all of these. So redox is much more general. It's any time electrons are lost or gained, you've got redox. But these are a little bit more specific. And that's chemical reactions. So 1, 2, 3, 4, 5 main types that are new. Redox we've already done quite a lot of work with. The big idea is balancing equations, making sure that you've got equal numbers of reactants and products. The numbers and types of elements that you have to be equal. And you do it by balancing this way. And the way to get proficient at this is to practice, 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 which we will do a lot in class. And also, a lot of these reaction types we'll do as experiments in the next couple of weeks. And that's it.